Thank you. I would like to thank the organizers for bringing different groups of people to this place, to this beautiful place. And I will try to indeed to suggest some semi-philosophical questions which maybe can contribute to strengthening the connections between two well-developed areas. One is ergodic theory and one is, let me call it, linear dynamics, especially hypercyclicity phenomenon. And so I want to start, so the whole general idea for what I want to suggest is that many dynamical systems, and by this I mean objects of the form xt, where x is compact and t is homeomorphism, or say th, I write it in opposite order, but this is say Hilbert space, and this is a say hypercyclic operator, or my favorite object, measure preserving system. And in all of these situations, we of course study not transformation itself, but its orbits, its iterations. And then it was observed some time ago that along a pretty rarefied set of iterations, let's call them times, along rarefied sets of times, you still have pretty regular behavior. And this is mysterious in a way. And so there are some reasons to this. And some of these reasons connect to what we heard from Katalin Badea in his talk. There are special kinds of sets along which you have different kinds of regularity. And so I will give you some examples to justify this point. So I am especially comfortable with this setup. This setup actually induces plenty here because of presence of invariant measures. That's classical Bogolubov-Krylov theorem. There are results in purely topological dynamics which actually is of interest to establish without invariant measures. This is especially relevant to linear dynamics, when there are recently a lot of interesting applications of introducing of invariant measures, but there are still things to be better understood in case you don't have good measures. So I will start with some simple examples which should be clear to everyone. And please ask questions. I love questions. And when I teach, I sometimes tell students that I make intentional mistakes, and if they catch me, they will get better grade. And it turns out that mistakes are not always intentional. But if students catch me, I'm always happy. So in any case, so example of what I'm talking about is beautiful Furstenberg's generalization of Poincaré recurrence. So we all know what is Poincaré recurrence. Let me just Poincaré recurrence theorem. So for any measure preserving system x, b, mu, t, for this discussion, this is probability space. And t is, of course, measure preserving. And for any A in sigma algebra of positive measure, there exists n such that mu of A intersection T and A is positive. So that's totally classical result. And from today's point of view, rather trivial result. So it's really immediate consequence of pigeonhole principle. I don't know, maybe I will not have time for any serious proofs, but this one I can prove right away so that everyone is comfortable. And I'm sorry, maybe everyone knows it, so, but I still will do it. I think it is this one. Not really. Okay. And so prove So consider these sets A, TA, T minus IA, T minus JA, and this is half of the proof. And then, so by pigeonhole principle, there exists I smaller than J such that T minus IA, T minus JA measure is positive, and this is the same by measure preservacy as this, and this is end of the proof. This is your N. So it only surprises us how such a rather trivial result can be so useful, but it is. And why? Because it uses, indeed, if you analyze it, it uses only finite additivity of measure, and it uses pigeonhole principle, and these are most basic things that you have. By the way, there is a very nice paper by Hennenfent, one of the classical mathematicians who contributed to Poincaré recurrence as well. And his survey paper is about the power of pigeonhole principle in number theory. And it's amazing how much you can get in classical number theory just from pigeonhole principle. And this partly applies in other sciences. So in any case, if you analyze this proof, it's not clear what is the structure of such N's, besides one simple observation, but it really leads to already something powerful. So I could take, instead of this sequence of sets, I could take sets of the form Tn1a, Tnja, Tni, Tnja, and it would lead to something like this. This is totally the same proof, just you take any sequence of iterates, and then the differences will be good for recurrence. But because there are so many sets of differences, it already tells you that those N's which return your set is a very massive set, because it intersects. So corollary of this whole business is, so the set of N for which measure of A, Tna positive, intersects any set of differences in a non-trivial way. That follows from this observation. But if your set intersects any set of differences, it has to be very large. It has to be of positive density. It has to be what we call synthetic, namely has bounded gaps. That's already plenty. And it's only still same small idea. Okay, so what Fürstenberg added to this, and this doesn't follow from this analysis. So Fürstenberg, so there exists N, so that measure of A intersection. So there is recurrence happens also along polynomials. I wrote it for N square. It's true for any polynomial with integer coefficients having, say, 0 constant term. It's even more general than that. Now, that's already surprising. Because squares is an enormously structured set and small set. And why should, in dynamics, you always come back along squares? Mystery. And it definitely doesn't follow from such simple proof. I know at least 2 different proofs of this, but both are not so trivial. Now, it's equivalent to the following beautiful result, and I will just mention it, and I will stop mentioning number theoretical or additive combinatorics applications, but that's the driving force for many of these things. So this result, which, by the way, doesn't assume anything, right? It's ergodic language, but that's maybe general mathematics, because what are the quantifiers? For any measure-preserving system, for any set of positive measure, there exists N. And so here is another result, which is Sarkozy. And it says that if A is, say, let's call it E, is in N, and density of E, which is by definition lim sup of E intersection one n positive, then there exists x, y in E, there exists n such that x minus y equal n squared. Equally surprising. So you have large set, all right, it's a set of positive density. You don't assume anything else. Now there is a small set of squares. Why should be there always 2 points whose distance is perfect square? I don't think it's possible to guess, but it was conjecture made by Lovas based on some graph theory considerations. It was later proved by Sarkozy, and Fürstenberg gave independent proof by using ergodic theory. This is the same result. I can derive one from the other infinitely many lines. So it's not like in logic that any 2 correct statements are equivalent, okay? And so it is this phenomenon which we would like to understand better. So the most basic thing is recurrence. So application to original Poincaré ideology was, so why was he interested in Poincaré recurrence? Because of his quest for stability of solar system. So if you have a set of positive volume in your finite measure phase space, typical point will travel, and come back. Now this shows that it will come back after exactly quadratic number of seconds, okay, or cubic. And you may start right away asking questions, okay, so if this happens, what are those sets for which it happens? And now it's totally hopeless to give characterization of such sets, but there are different, not always the same reasons for this. So I will move now to even more maybe physically interesting thing, which is ergodic theorem. So let's see if there is this kind of phenomenon there. And so okay, now so classical, say, for Neumann's theorem, so classical ergodic theorem for Neumann is that if H is a Hilbert space and U H to H is unitary operator, then for any f in H, 1 over n, U n f converges to projection is orthogonal projection on this subspace and sorry again, it's totally classical and well-known result, but now in vein of our philosophical line, so other smaller sets, other rarefied sets for which it will be equally true. When I say equally true, I just not only care about convergence, I want to, for convergence to be to correct limit, and this is correct limit. So in x, b, mu, t set up, so take uf, so you take h to be L2, and UF is what is induced by T, and so if P invariant is trivial, only constants, this is called ergodicity, then 1 over n f of t and x converges to integral of f d mu. And this is classical ergodic theorem, which tells us that time average equals space average. Okay, so that's the most powerful principle in many areas of mathematics, if you interpret time average appropriately. So this is time average, you measure every second, and this is space average. And they are the same under ergodicity assumption, and this is if and only if. And this was von Neumann's discovery. So what Maxwell and others were interested in statistical mechanics takes place only under ergodicity assumption, and ergodicity is necessary and sufficient condition for time and space averages to be the same. All right, so here's a theorem which supports this line that there are some mysterious rarefied sets for which such things still happen. For example, for any c bigger than 0, c not in n, 1 over n u n to power c integer part goes to correct limit. C not in n. I think I said not in n, but didn't write not in n. Not in n. Okay. How about this one? It's also true. You take p, the primes, and you order them in natural order. And then it turns out that this is also true. Of course, we talk here in norm. So, phenomenon exists. There are special rarefied sets. Who knows how general is this phenomenon, but there are many, along which things happen the same way. So let me clarify. So what you should ask at this stage, and how about ergodic theorem along squares, right? If along squares you have Poincaré recurrence, is there ergodic theorem along squares? And so here is a result which answers this question, and I will formulate it in a special case. Oops, that's the wrong one. And I need this one, I guess. So I thought nothing happens, something happens here. Okay, and so for any unitary operator which maps Hilbert space to itself, you can have various decompositions. One decomposition we saw already before. So H is H invariant plus the space where the limit is 0. That's exactly a reinterpretation of ergodic theorem which I formulated above. But you can make more splittings, and they are all interesting. You can keep enlarging this space, and it will shrink this space, or make your result stronger there. So the very first such splitting would be H, I call it rational, plus F, where 1 over n uin f goes to 0 for any I, and of course for any I. So what this decomposition, so if before this is called sometimes ergodic decomposition, this may be called totally ergodic decomposition. So this space can be called, rightly so, H totally ergodic. And on this space, on H totally ergodic, every power of U is ergodic. So let me write it this way. Every power Ui is ergodic. That's the gain. So you put here, and so what happens here? So this is just span of those f for which there exists I, such that UIF is f. Well, when I say span, I mean closure. Now, pay attention at quantifiers. So here there exists I, and here for all I. So this decomposition actually is corollary of this decomposition. If you apply this decomposition for all i's, you intersect in one place, you unite in the other place. So what is corollary of all this thing? So it's corollary of not just Hilbertian analysis, but also much finer measure preserving analysis, and this is a result of Bourgain. So what Bourgain proved, it's a special case, but it's very significant. So if Ti is ergodic for any I, then for any f in LP of x, where p is bigger than 1 over n, f of Tn square x converges almost everywhere to integral of f. And so this is what I call paradox of lazy physicist. So physicist is sitting in his lab and wants to check on average behavior some parameters of his dynamical system. So he is supposed to study it by taking measurements every second. And then it's ergodic theorem. Pay attention, this is a very strong form of ergodic theorem that's almost everywhere. Much more subtle result. And now, lazy physicist does measurements every quadratic second. And he will still get the same result. And it's not easy to explain this paradox. At least from physics point of view, I don't see how to explain it at all. I can analyze mathematical reasons for that, but why should a physicist expect this to happen? And now, by the way, I'm not a physicist, so whatever I will say now, maybe it's only mathematicians' attempt to analyze it. But if you have general physical system, usually, and in older times, they would consider continuous time. Now, there is a notion in mathematics which is called ergodic decomposition. So it is really without loss of generality that you assume that your system is ergodic. You just concentrate on n invariant ergodic measure. And now, if you want to do measurements not continuously but every second, then you should pick up some scale in your ergodic flow and start measuring it every second. Now, it is an easy remark that for ergodic continuous flow, typical fixed element is totally ergodic. And so if I took a totally ergodic element, I will have this result. And I can start saving on measurements, because along squares, it will be the same result. So why? And now, what is so special about squares? Well, not too much special. Any polynomial is good for that. And many other interesting, as they call sometimes, arithmetic sets. Many random sets are good, but I don't know if you want to trust randomness. You know, the same physicist can start tossing a coin and will do it every quadratic second. So it will be still correct, but I don't want to depend on his tosses. However, it's totally deterministic. Okay, now let me move then to, at least for now, to linear dynamics. So let me make a definition maybe. And so definition is a set A is HC set. You can guess why HC. If for any hypercyclic T. By the way, I restrict to Hilbert space because that's the only one I feel more comfortable with. This definition can be made in much bigger generality. So I take any hypercyclic T. There exists X in H such that Tn X n in A is dense. So it's natural definition. It can be thought of analog. So this Poincaré recurrence along squares leads to natural definition of sets of recurrence, right? Those sets along which Poincaré recurrence is true. Actually, Furstenberg originally called such sets Poincaré sets. And then here we talk about HC sets. Do we have any non-trivial examples? So I have only one non-trivial example. So example AN. How do I know that this is an example? That's Ansari theorem. So there are people here who know much more than me, but so it is a beautiful result of Ansari, which says that if T is hypercyclic, then any power of T is hypercyclic, right? If that's the case, this is HT set. That's my first question to you. Can you enlarge significantly this family of sets? Any other interesting HC sets besides infinite arithmetic progressions? How about I'm afraid to ask about squares, but at least I can ask about alpha n integer part. Is this a HC set? I don't know. So speaking in dynamical terms, if you think of this as topological dynamical system, it's not just transitive in case of hypercyclicity, it's totally transitive. Now, if it's totally transitive, maybe there is a chance that alpha n sets will be right. Now, in finitistic situation, in compact situation, that's not necessarily the case, maybe. You can, take irrational rotation by alpha, and then alpha n integer part, if you rotate by 1 over alpha, you may destroy things. In any case, I have now next question, which is related to linear dynamics, because my goal was to connect this area. So we know there is one very powerful method in linear dynamics that's to introduce invariant probability measures, and if they are of full support, and especially ergodic, then by the way you have, so let me at least claim it as a remark, there exist many hypercyclic operators such that Tn squared, such that for some x, T in space, Tn square x is dense. How do I know this? And I can give you many other sets along which it will happen, but how do I know this? Well, in a cheap way. So I will take my hypercyclic operator to come from measure-preserving system, which is ergodic. And I can make it maybe weakly mixing, if I'm lucky, and this is possible today. And then whatever weak mixing gives me is much more than that. And so for classes of hypercyclic operators, there are definitely those HC sets of quality. But I want it to be universal. By the way, it is a valid question. So for different classes of measure-preserving systems to see which rarefied families are good for recurrence or for averaging behavior. So that's why this is applicable to linear dynamics as well. The bad news are that then it's maybe not so exciting, since it will be transport or transfer of knowledge from ergodic theory to linear dynamics. And in ergodic theory we have plenty, so just transfer and be happy with funny operators. But in big generality, this remains very interesting to me and a challenging question. And so in this direction, I have the following semi-question, semi-conjecture. And I never saw anything like this in literature on linear dynamics, but I'm outsider, so maybe you know better. But my question is, let me maybe write it on the blackboard somewhere. Question. So assume that T is hypercyclic. Is there a potentially infinite invariant measure, maybe? Okay, invariant measure of full support, which, so to say, explains the HC phenomenon. And since I'm outsider, I can ask such questions. This would be nice. Sometimes you're lucky and you have finite invariant measure, and that already gives you plenty of examples. But suppose I have general phenomena. Maybe for very general phenomena, at least there is an infinite invariant measure. And then I would have still plenty of hypercyclicity phenomena because of ratio ergodic theorems. And for denseness and other things, that could be enough. So if my measure is conservative, I had to add it here. So conservative. And by the way, somehow to connect it to Ansari theorem, that's an exercise in infinite measure theory, that if you have conservative transformation, every power is conservative. So this is typical wishful thinking of outsider. So maybe phenomenon of hypercyclicity is adequately explained by infinite invariant measures. In lucky cases, you have finite invariant measures, great, but maybe you always have infinite invariant measure. Now, this leads to natural questions about sets of recurrence for infinite measure preserving transformations. Besides this, do we know anything? Same question. Same question. Okay, any questions so far? Because I'm trying now to move to my other favorite topic, and it will be maybe less friendly because it will involve idempotent ultrafilters and other things. But I will try to make connections between that area and linear dynamics. So far I tried to be as friendly as I could. So any questions? Yes, please. Rotation on a few points. So, and that's the only, so that's this rational spectrum business. So, and that's a really trivial thing to agree in advance not to worry about, right? So you have rotations on finitely many points, that's a rational spectrum. And you go to ortho complement of them and you have nice life. So in general, by the way, also want, so the moment you are totally ergodic, you have plenty of those phenomena in clean way. For example, N alpha mod 1 is uniformly distributed for any alpha in Q. That's well-known result. But it's equally true that n to the power k alpha mod 1 is uniformly distributed. And this is, of course, a result of while, very classical, but this is the same type of phenomenon if you want to think it this way. So you go to very rarefied subsequence and it's still well behaved. Now here is another, if you want to be even more impressed, take nth prime, fixed power, is also uniformly distributed for all alpha. will be glad to hear it.
For every recurrent point, you can generate an infinite measure.
But I still want this measure to be conservative and of full support.
Conservative it will be, but full support is trivial
Because denseness.
Yes.
We're in business. So well, I hope you're not cheating, but in any case, that's exactly what is nice. If this is the case, then we have measure-preserving explanation of hypercyclicity phenomena.
You know what you think? There's Glim-Efros, which tells you that when you have a homeomorphism of Polish space and you have a recurrent point, then you induce an adding machine. An adding machine is unique, it's a sort of rotation, addition of one on the group of dyadic integers, so our measure is an invariant probability, and your process
Is a suspension.
Be a tower,
A tower.
which is naturally conservative.
I feel good. Okay. But this still phenomenon of lazy physicists now has new sort of reformulation. How about lazy hypercyclist? So I still would like to know about sets of convergence, recurrence, of averaging in infinite measure-preserving systems.
Electric hypercycling.
Well, eclectic hypercycling. So in any case, I really think that now those questions become even more interesting because they would serve both the hypercyclic community and infinite measure community. Okay, so back to this. I'm surprised that no one is surprised. That's pretty non-trivial. You take nth prime to k's power, and it is uniformly distributed. This is a result by Rin, which is a generalization of all the result of Vinogradov. So in many theorems, yes. So if you look at these theorems, they also, if you care to use a spectral theorem, these results are corollaries of uniform distribution results via spectral theorem. Now, in measure-preserving ergodic theory, we are interested in multiple recurrence. Some of these sets are sets of multiple recurrence, and there spectral theorem is useless. So there should be some other reasons still for this phenomenon of regular behavior, say averaging behavior along the sets, which really extends to generalized correlation functions. This is something I will not touch, but let me go back then to what I was planning to, this IP sets and idempotent ultrafilters. So I think I can erase here. Okay. So what is IP set? Any set of the form, or sometimes they call it finite sums set. Is the definition clear? So this is generalized semigroup. XRNs are, if you wish to think of them as generators, and then you're allowed to take sums of any finite subset of them. We don't allow to take multiples. So x plus x is not there, but xi plus xj for different ij will be there. And this is, let's call it approximate semigroup or whatever. And this is very, very rich type of sets, because there are many of them, and there is a beautiful theorem by Hennenfent. And it says that for any finite partition, or as they say sometimes, coloring, one of CIs contains an IP set. And of course, it is at least. Okay? So, by finite partitions, you cannot destroy this highly organized structure. By the way, they are called IP sets. It was suggested by Furstenberg and Weiss to call them IP sets because this should be reminiscent of either infinite dimensional parallelepiped. And I think there is this feeling when you think about there's some cubic phenomenon there, right? Or idempotent. I'm not sure they had in mind idempotent simultaneously, but idempotent, that's what is behind it now. Which idempotence? Well, the key to Hennenfent theorem is the beta n, the stone check compactivity. Let me write it. The key to this is beta n, which is for us the same as all 0, 1 valued finitely additive probability measures. On all the subsets of integers. So, I don't know, in Europe they study this object, right, in undergraduate studies. In the US they don't study it even in graduate studies, unless you take special course in topology. This is nothing but stone check compactification of integers set with universal properties. But it is also very interesting for applications in Ramsey theory. And so I will come back to this, but for now I want to introduce a notion of largeness, which so a set A in N is called IP star if for any IP set A intersection is non-empty. So we had a similar example before. You remember sets of returns in Poincaré recurrence are intersecting non-trivially with any set of differences. We call sometimes such sets delta star sets. But this is a little bit more subtle, and it turns out that this kind of property is way more natural in multiple recurrence. So in any case, so exercise is that if A1, A, K are IP star sets, then A1 intersection A2, AK is also IP star set. Now that tells you that this is very, very strongly large family of sets, right? So any two intersect, any K intersect. This is corollary of Hennenfent theorem. So it's exercise, but you have to know how to approach it. If you're outsider, it will take some effort. But why do I mention these sets? Because this is yet another very natural family of sets for which you can start studying analogs of frequent hypercyclicity. So you can call, so I don't know, let's call it IP star HC property if n's for which Tnx belongs to open neighborhood in your Hilbert space is IP star. So I have quite a strong feeling that it fits. So there is this hierarchy of this frequently hypercyclic, upper frequently hypercyclic, reiteratively frequently hypercyclic, and then it will be somewhere inside this, on one of the ends, IP star hypercyclic. Yes? Yes. So here, many quantifiers are missing. T is hypercyclic operator, and U is any open set. Okay? Now, the key to Hennenfent theorem is this space. And so I think I still have, how much time I have? 5 minutes. So then I will just very fast tell you that there exists operation. So we denote these measures by small letters P, Q, R, S, T. And instead of saying that measure of a set is 1, I will say that set belongs to P, namely has measure 1, and then P plus Q so P, Q going to P plus Q, and it's defined like this: A belongs to P plus Q if and only if all n for which A minus n belongs to P belongs to Q. This is pretty forbidding type of formula, but for those who like harmonic analysis, this is nothing but convolution of measures. So it's really very natural object. And so by Ellis lemma, there exists P such that P equals P plus P. And this is kind of ultrafilters which are just right for doing ergodic theory. And so I will give you examples of this, why it is so good. Yes, by the way, I forgot to tell you that those ultrafilters, there's a measure. So you can say that P lim of xn is x if for any epsilon, suppose it is in a metric space. For any epsilon, the set of n for which xn belongs to open neighborhood is P large. So I could alternatively write this. I hope this is clear enough notion. One of those many types of generalized convergence. So you're very close to your x, u sub x is neighborhood of u, and this is for any u. I said epsilon, so let me put it for any ux. Okay, so you converge to point x if you enter any neighborhood in fullness. So the set of indices for which you're there is of p measure 1. And so here is so let u be weakly mixing unitary operator. And it means that many things, but it means in particular that UNF G goes to 0 for any f and g, as long as n goes to infinity and n does not belong to set E of 0 density. And alternatively, U is weakly mixing if and only if, long list of equivalent conditions. Those more functionalistic are that there are no eigenvectors. Von Neumann and Koopman introduced this notion, and they postulated that there are no angular variables. That's what it is for physicists, absence of eigenvalues. So, sorry for cutting some corners here. Weak mixing is the most interesting notion in ergodic theory, in my opinion, because it's mysterious. There is this special set E which has to be avoided. That's why it is weak mixing. For no exceptional set E, this is strong mixing. But typical measure-preserving transformation is weak mixing and not strong mixing. That's classical result of Rochlin and Halmos. And so equivalent definition, yet another equivalent definition. How do you like this one? And this corresponds to what I was talking at the beginning. This is equivalent to weak mixing. You just restrict to squares only. Yes? I assume that it is weak mixing. So what do? What? For every FNG. I could take F and F, by the way. This is equivalent. But so in any case, how do you like this claim? I forget about the rest of integers. I go along set of zero density n square, and then it is a further subset of zero density of n's, which I have to avoid, and I still have exactly the same phenomenon. So this really justifies our belief in measuring every quadratic second. You know, even in weak mixing, you still have weak mixing along squares, and squares is a set of zero density. That's why it is surprising. In any case, so for a typical weakly mixing operator, there exists P equal P plus P and Q equal Q plus Q in beta n, such that P lim UNF equals F for all F in H, and Q lim UNF is 0 for all F in H. And here it is weakly. And so I suggest to look at this formula, and I will spend the last minute, half minute, minus minute, to just discuss this thing. So this is a suggestion for novel notion of chaos. Just look at what I wrote there. So there exists a special sequence indeed. The sequence generates a idempotent ultrafilter, along which you go weakly to zero. Sorry, you go weakly to itself. That's what we call rigidity. And this should be for weak mixing relatively rare phenomenon because of exceptional sets of zero density. And then simultaneously with this, along some other ultrafilter, you will go to zero, which you expect from independence phenomenon in dynamical system or in linear dynamics. And that's what I suggest as a generalized notion of chaos. If you have periodic functions in classical notion of chaos that we heard about yesterday, of course it will satisfy this. But for typical weak mixing, it is coexistence of two modes. One is, you may want to call turbulent, that's going to zero weakly, and one is laminar, you go back to F itself. And so I believe that this notion of chaoticity can be nicely implemented in the framework of linear dynamics. And maybe I would stop here. Thank you.